This is the first section of a fairly large lecture on chaos theory based on lectures I gave in January of 2017 to Peak to Peak Charter School physics students and math students. You'll see my contact information here if you want to write to me and point out mistakes or ask questions. So let's get started. Sorry. The lecture's in multiple parts. Probably will not get more than a half of part one into this single video, but let's just dive in. So we're going to be talking about something called a utility function, and not to be worried about that. I'll explain it in a lot of detail. So here we go. First of all, this whole lecture is about chaos. So what does that mean? So chaos describes nonlinear systems that where there's some relationship between the input and the output. For example, if we put an electronic signal into a telephone, we expect to hear sound come out of the speaker of the phone. So the electrical signal is the input and the sound signal is the output. Almost all the systems we encounter, whether we're talking about driving a car or operating a computer or flying an airplane, all involve relationships between input and output of systems. Not all of them are electronic, of course, and we're going to talk about another kind of system that has no electronics at all, and that is the topic of population dynamics. But I don't want to get too far ahead. So there are circumstances where the output of the system looks random, just unexpected results compared to the input, and we're going to study those kinds of systems. We also have to say that if you design a system and it has properties of chaos, or it's chaotic, and you run a particular experiment over and over, you'll always get the same results. But if you change the input even the tiniest amount, you will get something completely different in the output. So I know this sounds a little abstract, but we're just getting into it. So you might want to come back and reflect on these statements as we get some more experience. So one of the fathers of chaos theory, Ed Lorenz, said chaos is described when the present determines the future, but the approximate present does not approximately determine the future. That means if you have even the slightest uncertainty about the current state of a system, the future state will be completely unpredictable. Ed Lorenz was a meteorologist, and he applied these concepts to predictability of the weather. So once again, we're dealing with systems where a tiny change in the input can lead to a dramatic change in the output, and we'll see through the lecture many, many examples of how this works. Why do we study it? Well, nature is nonlinear. There's all sorts of complexity in nature. We're going to review some of those during this lecture. And because nature and the world we experience has these nonlinear properties that can lead to chaos, this is a worthy topic of investigation. It's also true that scientists and engineers going through a curriculum in high school and college are almost always working on linear systems. Those of you who have studied, for example, the simplest machine conceivable, which is a pendulum, know that in order to solve the equations of a pendulum, we choose conditions so that we don't have to deal with nonlinear behavior. I'm going to show you what happens here in a second when you have a truly nonlinear system. But the typical experience that students have is we're always dealing with linear systems. The input and output are related by a constant. That's the way nature works. So let's look at a different kind of pendulum. This is a double pendulum, and here it is. So you see there the lines being drawn by the tip of the second piece of the pendulum, and you can build one of these pendula. You can buy a kit that has very low friction bearings. You can make sort of a scientific toy. You can hang it on the wall, and you get it started. And as pointed out here, starting from a slightly different set of initial conditions when you start the pendulum will lead to completely different trace over here and how this. So it's going to start again. So we say those lines will be the same for this because this has exactly the same initial conditions every time. It's a computer simulation. But in real life, there's no way to reproduce the initial conditions. You'll always end up with something dramatically different. This is an example of a chaotic system. So let's now talk about something that's in the title of this section, the logistic equation, or sometimes called the logistic map. And it has this property. Those of you who have recently taken a math class or algebra class, if you think through this, you'll see this is really the equation of a parabola opening downward. And the way this equation works is we pick an initial value, n, for some parameter. And we have this scale factor r. We're going to be talking about r quite a bit. But we pick an initial value for n, and this equation produces a value for a future state called n plus 1. Then we use recursion. That is, we take this result and we put it in here and here. So we take the result and run the equation again, and we get a new value over here. And we put that one in and run it again. I'll explain why you might do that in a second. So here are two examples of the logistic map for two values of r. And what we do is to keep everything looking graceful so that all the values here go from 0 to 1 and all the values here go from 0 to 1, we restrict r to be somewhere between 0 and 4. So let's see how that works. If the first value is a half, then this 1 minus a half is a half, and this is a half. So a half times a half is a fourth. And if we have r equal 4, 4 times a fourth is equal to 1. And so we would get a result of 1, and that's this point right here. If we started with a value of a half, once again we get these two multiplied together give us 0.25. But if r is equal to 1, then this result is 0.25. That's why we'd be here. So the question is, why do we care about the logistics map? And here's why. First of all, we already observed it's a parabola opening downward, and it involves recursion. We use this equation with recursion. And we restrict r from 0 to 4. And in most cases, this index n that's going to increment from 1 to 2, and then you put it back in here, n plus 1 is 2 here, it's going to be 3 there, and you keep doing it. That's kind of relates to the time evolution of a system described by these curves. And for evolutionary studies, and you might have, the increment might be in millions of years, and for electronic systems, it might be in microseconds, but what we're thinking about here is population dynamics. So let's talk about the logistics curve. Here's an example logistics curve, the red. And let's imagine that we take a field, put a fence around it, and put a number of rabbits in the field. And in January, we put the rabbits in the field, and we come back in June to count the rabbits. So let's say we started with 8, and we come back in June, and we now find that we have 11 rabbits. Some were born, some died, and so forth. So if we had started here with 8 rabbits, the logistics curve would tell us that we would have this many rabbits. So kind of mentally draw a vertical line at A. So I have more rabbits, presuming that the birth rate exceeds the death rate. Once we have that value, we would take that value and go back to this line here, which represents the population when we make the measurement, and we could guess that the future population is going to be bigger. So if we started with 8 rabbits, and then next time we checked we had 11, and the next time we checked, now we have 11 rabbits participating in breeding, we could expect to have more than 11 rabbits. So we kind of walk up this curve, and the question is, how does the behavior of this curve describe that population? So what it shows is, if you have a small population, you can expect the growth. You can have growth in the curve. As you get to a larger population, where this represents half of the maximum population that can ever be supported by the fenced area, when we get to that point, we have a maximum population. If we add more rabbits, either by birth or we just deliver them in cages, the population is going to go down because the resources in the pen don't support a larger population, where the rabbits would be have scarcity of water or food, or large quantities of rabbits maybe breed disease, and so there's an issue. And if you went right up to the maximum allowable number of rabbits, the next time you come back, they'll all be dead because they exhaust the resources and starve or run out of water or whatever. So we want to study how this logistics map behaves under different conditions of the reproductive rate of the rabbits. And let's go back, and that's what this R stands for. It's a simplified mechanism for describing how successful the rabbits are at growing their population. All right. So, and the blue curve will be explained in a second. So let's review what we're going to do to use the logistics diagram. We start with a number of rabbits at A. We use the formula, here it is, to compute the value that we can predict using this curve, that we're going to have a different value next time we make measurements. And that's what this arrow shows, that we started with a number of rabbits, A, and the logistics curve said we'll have more in the future. Now we take that value, as I described earlier, you could take that value and go over here, and because we're doing recursion, you would put it in and start again, and you have a new value, and then you pick that point and go here and so forth. But there's an easier way, and that exploits this blue line. Everywhere on the blue line, X and Y are the same. So if we have this value right here for the second time we measure rabbits, to graphically determine what we'll have in the future, we just go horizontally, and that point right here at the tip of my cursor is the new population. So let's do that. And we can repeat the process. And now we don't have to keep going back to the horizontal axis. So this is how the population grows as we keep checking on the number of rabbits in the pen. An interesting thing starts happening here. The growth, actually at this point, this is probably the sixth step in the measurements we make of the population. We now see that we've gone past the maximum population for the growth rate we've chosen here. Now we go over here, and we're actually going to see, we could expect our next measurement, we're going to see fewer animals in the pen. And we go over to the blue and up, and we end up circling this point right here. Now, I didn't mention the value of R we chose here. It's actually equal to 3, and the first value we chose is 0.04. Now remember, On this scale, 1 represents the maximum population. That could be 100 rabbits or 10 million rabbits if it's a big field, but we can eliminate that factor by saying what fraction of the maximum did we start with. In this case, 0.04. And if we follow this map around, touching the blue curve, then the red, then the blue, then the red, after 10,000 iterations, we find that the population is somewhere between these two numbers. It bounces back and forth. That is, the population goes into orbit right here, not necessarily centered on this point, but it's kind of trapped right here. It just keeps orbiting that point. And so let's look at an example where R is small. That is, the growth rate is small, either because the rabbits are not interested in having more children, or there's disease or predators or something. So now the curve, instead of going all the way up here or being here, is now pretty low. And let's observe something graphically, that there's only one place where the red and blue curves touch, and that's right here at 0. If we go back to the prior case, they touch at 0 and this point, but not here. Because this growth rate is low, they only touch here. So if we now explore, start at 0.8 for the initial population, we come up, we touch the red curve, we go to the blue, and then we go down, and you can probably guess that we end up at 0 population because we have a low growth rate built into this model. So here's detail of this part of the curve, and you can see it just kind of rattles around here and heads for 0. So for low growth rate, after a few visits counting rabbits, we're going to find 0 rabbits just because their inherent population growth rate is too small. Now here's the math. So here's our logistics function, and for those who are familiar with calculus, here's the derivative of the logistics function. And we can, from this, we can calculate the maximum slope which occurs when the starting point is approximately 0. So we already can see that to do these kinds of analyses, having some skills with calculus might be helpful. We'll do more of this in a few minutes, but if you're not familiar with calculus, don't give up, because virtually everything we're going to do from this point forward is just algebra. All right, so now we've explored when R is less than 1. How about when R is in the range of 1 to 3? So this looks like the first one we did. Here's R 1.7, here's R equal 3. And if you do this one, and it doesn't matter where you start, but we just randomly started here. You see we rattle along here, and if you follow this, you'll end up right at that point of intersection. If you choose R equal 3, we already did this, you will orbit around the point of intersection. And that gives us some clues about what's going to happen as we look more deeply. So here's the equation of the blue line. It's just linear, y equals x. Here's the equation of the red curve. This is the logistics map, and we can do a little algebra here. And we can see that they intersect at this point. The point of intersection is at 1 minus 1 over r. So one of the math, and so the intersection here, if we apply this, you'll see for R equal 3, the intersection is at 0.666. Remember that earlier we had a result that orbited around this point, 0.666, right there. For R less than 2, you can sort of do this problem in your head. For example, when R equals 2, 1 over 2 is a half, 1 minus a half is a half, so the point of intersection would be right here for R equal 2. And you can do simple numerical experiments to see how these curves intersect. Okay. Now, I'll just warn you ahead of time when arg is bigger than 3. So here we're only doing 1 to 3. When r is bigger than 3, things go crazy. And we're about to see that. So here's r equal 2.5. And this is the same kind of technique I showed earlier. I copied this from a reference right down here. So he did not use red and blue the same way I did. But nonetheless, if we start here, we go boom, 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 and we end up at the point of intersection of the two curves because r is less than 3. Now, if we go to r equals 3.2, so we see something very interesting. No matter where we start, we end up with two values. That is, once you get into orbit here around the intersection point, the lowest value you'll ever see is here, and the highest value is here. And no matter how many times you run it, you'll just bounce back and forth. That is, when you visit the rabbit patch, you'll either measure this number of rabbits or this number of rabbits because their population is grown to a point where if you have too many rabbits, the population collapses a little bit, and then they can be rebuilt, and back and forth it goes. So there are two values when r is equal to 3.2. Now let's go to 3.5. Similar thing happens. If you run it many times, you'll then find there's 4 values. There's a maximum population, a minimum population, and 2 intermediate populations. And if you follow this curve around, which we are going to do, you just keep going around and around, touching the lowest population, the highest population, and 2 intermediate populations. All right, so here we have, I'm just highlighting the arrows, 4 different values. So we've started with a modest growth rate. You'll just have one stable population. If you raise the growth rate, you'll have 2 values, and then 4. And then the question is what happens next? And this is what happens next. When r is 3.8, it just goes crazy. You can never predict what you're going to find if you go out to count the animals. You might find an amount of animals near the maximum allowable, or you might find a number close to the smallest, and every other possibility. This is the so-called chaotic situation. And it happens using the simple model for the logistics map at r equals 3.8. All right. So here's what I have done in doing some explorations. Here I've picked r equal 2 and the first value of 0.04. And this horizontal goes from 1 to 10,000. I did 10,000 experiments. That's what the black arrow shows. And if you follow it very quickly, as you do the experiments, you settle into this one value that just persists forever. And that's equal to a population of 0.5. If you raise the rate, the r value, to 2.5, you also get a stable value, and it's at 0.6. And if you go look at the equation we derived, you'll see that that's in fact what you should expect. Here's what happens when r is 3. If you only do a few samples, it bounces back and forth between these two, and it gradually settles in. Remember, I've done 10,000. By the time you get out here, I've done 10,000 iterations. You just have the 2 values, and we already saw that in the previous slide. When r is equal to 3, you just oscillate around a value of 0.666. And this is just a note repeating what I've been saying. Here's r equal 3.2. Now you still oscillate between 2 values, even if you try it 10,000 times. And here's 3.5, and now we see this 4 values that we saw in the prior slide. So it's pretty easy to set up a spreadsheet. If you contact me, I can send you the one I built. Here's what chaos looks like. R equal 3.7. And we just get values lurching all over the place, completely unpredictable what you'd find. So here's a convenient way to draw this. Here's R, which we've been talking about, ranges from 0 to 4. The most interesting things happen in this range here from about 2.5 to 4. And here's the output we get. So for values of R up to 3, we only get one output. We have stable populations. But right at R equal 3, we get what's called a bifurcation. We split. So let's go back. Here's the kind of bifurcation thing we're talking about. Two values can exist. So imagine drawing a vertical line for any particular value of R. Wherever that line touches this set of curves, that's what population we would have. So if we were at R equal 3.2, we could expect a population here. Next time, down here. You can't tell which will be which. It could be this point twice in a row or whatever, and then unexpectedly it's down here, but you'd have two values because you just imagine a vertical line here. And that persists until you get to right here, 3.45. Now at this point, any value for R greater than 3.45, if you draw a vertical line, you're going to get 4 values, 1, 2, 3, and 4. And that persists until you get to 3.54, and now imagine drawing a vertical line through here, and you're going to have 8 values. And then when you get over here, it's just unpredictable. But one interesting thing to note is these segments of look like white stripes. We're going to talk about those more, particularly this one. I don't know if you can see right here, but there's something going on in there. We're going to show you some mathematical experiments that illustrate what's happening there. In the white spaces, the clue is here. In these white spaces, you see this? It looks very much like this. Sort of an echo in here. And no matter how deep you dig into these white spaces, you will see echoes of this. It's one of the odd things about the logistics function and its family of related functions. So the locations where bifurcations occur, here and here and here, are computable. There's some complexity in doing it, but I'm going to show you one example. So here's the example you saw before. Oh, actually, before we get to the math. So I'm showing different ways to present the data. We could do it this way. Logistics function and a straight line can show us how the behavior occurs. Or we can do a spreadsheet. We see a similar thing. Or we can have the bifurcation diagram. And I'm going to break here. We're going to stop this segment and